Okay, friends, good morning. And if you will recall that we had started plane problems last time, plane. And then I discussed with you the situations under which the state of stress and strain becomes plane. I mean, the three-dimensional problem gets reduced to two-dimensional in the natural way, provided those conditions are met. First one was plane stress, that is when the one dimension is very thin compared to the other dimension, and if the loads are all confined in the plane only. In that case, we get what is called a state of plane stress. Don't ever discuss there. Start with stress components, because I have seen this one. That is, this is the state which I explained to you last time. You take these 6 components of stresses, and then what will be 0? Under that condition, when the loads are all confined in the plane only, all these loads are acting in the plane, even if there are moments, they will be acting perpendicular to the plane and they will be coming out of the plane, but then they are all planar forces. In that case, state of stress at any point is like this. So, you start with this, and what happens, because there is no load in the z direction. So, this becomes 0, this will always be 0, these two. So, you are reduced only to 3 stress components that will remain non-zero, while strain components are not 3 and you get one additional strain component, that is because of the load in xy plane, the z dimension does get changed. There will be strain in the third direction, z, thickness direction. The thickness can change by a small amount. So, epsilon z is not equal to 0. So, you start with this. When you start explaining plane stress, these are the two conditions. Then you write down this. Then you say what will be 0. Don't ever discuss strains first. If it is a plane stress, thin sheet of paper, you start with the stress vector. Don't bring in the word strain in your discussion when you explaining this. So, then this state of stress we call plane stress. So, it approximates the 3-dimensional state of stress. Actually, the state of stress becomes 2-dimension, and 3-dimensional problem gets reduced to 2D. It is always good to deal with a smaller dimension, because your equations will be simpler, everything will be simpler. So, mathematics will be simpler. Then next one I am just revising. Next one we discuss this problem, that is a prismatic section which is very long in one direction, and that direction we have taken z. Prismatic means constant cross section. Beams are prismatic. This beam, for example, in front, above you, beam, rectangular cross section, we call cross section. If you take off the beam any place, it is the same cross section, B and D. Such a cross section is called prismatic. Prismatic cross sections not changing along the length. So, if you have a prismatic cross section, this cross section does not change, and then again there are certain set of conditions. So, this is a geometry, and then this prismatic cross section is confined between constraint. So, we gave the example of a dam. So, this is fixed in the length direction, in z direction at 2 points, this is constrained. And then the loading is such that loading is independent of z. The water pressure that acts on this is same throughout the length. Height of the water is same more or less, of course, with some undulation on the ground, but more or less, you are talking of ideal situation. So, it is the same load that acts along the. So, in that situation, what happens, barring the ends means there is a principle called Saint Venant's principle in theory of elasticity. Saint Venant's principle. It simply says wherever you apply the load or wherever there is a disturbance, you apply the disturbance, its effect will be felt only in the neighborhood where it is applied. Away from it, its effect dies down. This is the simple way of explaining St. Venant's principle. Anything, you apply a load here, yes, in the neighborhood maximum effect, as you go away, it just reduces, here its effect will not be felt. So, same thing here, what happens because of these supports, at the end your dam will be constrained, it will not be, it will be constrained to deform out of the in x and in y direction. But then in the most of the central zone, it will behave in the same manner. So, if you take any cross section anywhere, the behavior of this dam is similar. Every cross section behaves more or less in the same same way, same manner. So, this is also a two dimensional because it does not change with z. Behavior does not change with z. So, here we say we start with the 6 components of a strain and we find that out of 6 components these 3 strains become 0. Then we are left only with 3 strains that are epsilon x, epsilon y and gamma x y that are non-zero. Such a state of strain or stress corresponding, because once it is strains, stress also will be there, is called plane strain. So, do not ever talk of stress here. Do not bring in the word stress while describing a plane strain situation. Always have the 6 components of strain here. This is the mistake you do. Although I emphasize every year, every course I emphasize, but then when we see in the presentation it is not. So, from this you will find that this one is 0, this one because of constraint I think I have already given you the, this will always be maintained 90 degrees, this also will maintain 90 degrees. So, they become 0. You are left only with non-zero 3, non-zero. But then as before, when you come to stress, you will find there will be 4 stress components that will be non-zero, not 3. Strains are epsilon x, epsilon y and gamma x y, which are non-zero. So, these are non-zero, these are non-zero, but then stress you will find that there will be stress also in z direction. There is no strain in z direction, normal strain epsilon z is 0, but because of constraining, just like thermal problems, if you constrain a body, then and if you raise the temperature, there will be stress in that direction. So, normal stress will be there. So, the non-zero stress will be sigma x, sigma y, tau x y and sigma z. So, this again will be non-zero. Now, so this is plane strains. First bring in the strain, then you say from Hooke's law, this is what happens. Okay. So, that should be very clear. Then the third case, so this is also brings down, that is your problem, it brings out a fact that 3D problem, because dam is a 3-dimensional problem, 3D problem gets reduced to only 2D. Here also, you need not analyze a 3-dimensional problem of dam, but only a 2-dimensional problem, and you can get most of the quantities of for design. Then the last one that I told you last time was, I think this I have already explained last time very clearly, I think it is already there. What is 0 plane strain 2D? Last one I said is axis symmetric problem, axis symmetric. You have if I have an axis this and if I have this plane and rotate this plane around this axis, what I will get? I will get a hollow cylinder. such a solid is called axisymmetric. If I put the plane here, one edge coincident with the central axis, if I rotate this by 2 pi 360 degrees, I will get a solid cylinder. So, I can get similarly, if you rotate a line, you will get a just a cylinder, cylindrical surface. So, but we are talking of solid. So, any plane, any two dimensional plane you are rotating, so axisymmetric solid, axisymmetric problem. So, here what happens if the loads are also, so one is you get axisymmetric solid, and second one is if the loads acting on that are also axisymmetric. What is the meaning of axisymmetric? Independent of theta. Quantities do not change with respect to theta. Theta is this rotation. Axis is z axis, and then perpendicular to that is r, and this rotation is theta. So, I think this is what I have shown, z, r and theta, r theta z is your cylindrical quad. So, here again the problem, if it so happens all quantities become independent of theta, derivative with respect to theta of any quantity will be 0, and such a problem is occurs very frequently in real life. There are a lot of axisymmetric things that you see around you. All the nuclear power plants from outside, they will all be cylinder with some cap, spherical cap. All these storage vessels will be axisymmetric. Many well foundation I told you will be axisymmetric. But well foundation, does it act by axisymmetry? Is it solved as axisymmetric? Loading is not axisymmetric. So, structure is axisymmetric, but loading will not be, and if the loading is not axisymmetric, then the problem remains 3 dimensional. Then you cannot treat it as a 2 dimensional, no. Okay. So, loading, I am talking of axisymmetric problem in which both structure as well as loading both are axisymmetric. So, such a, now this the equations governing the axisymmetric solid. So, if you have some area that you are rotating about, this is your z axis and this is your r. So, this point is P, which is r z. And rotation is in the plan r theta z. So, the equations that govern this problem is, one is strains. How are the strains given? Here epsilon r, for example, will be, now any point P here will be, there will be a, can move in the r direction. So, let us call that as u. It can also move in this direction. In the plane, it can always move, but not out of the plane. There will not be any displacement of any particle P in theta direction if it is axisymmetric problem. It will move only like this, plane will. So, all the particles will remain always in the plane r z. So, every particle has got 2 degrees of freedom here, u and w, and for example, this one will be, so from your strain displacement relation, this will be this one, epsilon z will be equal to dw by dz, what are the other strain components? Epsilon theta, yes, epsilon theta will exist. I think I explained to you last time that every circle will change its radius. This particle, original circle, under the action of loads that are acting on it, what will happen? It will move, so radius is changing. So, there will be epsilon theta, and that is given by. So, there is a relationship that is available in your theory of velocity book, u by r, u is. Then the other thing that will be, what about gamma? What will be the change gamma? Gamma r and z. R and z, there is, yes, there will be, because any element here, original element, if you take a original element like this, after the loads are applied, this element will change its shape like this. So, 90 degree will be changed in the plane. So, this will exist. But other strains, other shear strains, that is other shear strains mean gamma r theta and theta z, gamma theta z. These will be 0. This 90 degree will always be maintained between these two directions. So, you have 4 non-zero strains component here, but still despite that it is, because this one no doubt it is out of the plane, epsilon theta no doubt it is out of the plane, but it is not a yes, the particle is not moving out of the plane, particle will remain in plane. So, if there is a original circle like this, any particle p, here was your point p, after the loads are applied, this circle becomes only a so this particle will move here p dash, and this will be your along u displacement. This displacement of this will be u, displacement of particle p. So, it will be 2 pi r change. So, 2 pi original r, let us say r plus u is the final 2 pi r, if this distance is original, I am taking r distance. So, 2 pi r plus u minus, so this is the circumference, minus the original circumference is 2 pi r divided by original circumference 2 pi r. You will find that this one will give you epsilon theta, and that is what will come out to be. You can see here 2 pi r will get cancelled, and then this will be 2 pi u by r will be left here. But this is not out of the plane. Please note that this is occurring because of change in the radius of particle is not moving out of the plane. Therefore, this is still a plane strain problem. Only thing is, because existence of this, we call this generalized plane strain. So, there are three types of these. Three are the types of problems 2D, and here again the problem gets reduced to 3-dimensional problem gets reduced to 2 dimension. Generalize. So, it is a 2-dimensional problem. Okay, so this is fine. Now, all these three types of problems can be treated in a similar manner when we have finite element discretization, because what we can do, basically you are having a plane and that plane which is rotated about an axis, or it is in plane stress, or this plane is in plane strain, general normal. So, this plane is, we are talking of only this plane. This plane can be discretized by elements of various types. So, you can have different types of discretizations depending upon our capability and type of elements that you want to employ. There will always be some approximation to the geometry that you will have to always, you cannot if you are using a triangular, for example, triangular element, and this is the geometry, you want to use this big element. So, this one actual geometry will have to be sacrificed. Of course, you make the element smaller and smaller, you can make this red color zone as small as possible, but that must be kept. So, there is always a geometrical approximation. So, this can be always we can have a geometry of so 4 noded, 3 noded, 2 noded. So, you can always, and each particle is having only a displacement u and a displacement v. Now, let us say now for all the 3 cases we will deal with only x y axis in the plane, although I had used r and z, r theta z for the last problem, but that also can be, you can always say. So that everything is in. So, you have u, and every particle p has got a displacement, it can move only in the plane u and v. So, the displacement vector here consists of only 2 components, not 3 components. Now, this we shall try to do plane stress first, because now we have come to see, we have been talking only about 2-dimensional problem so far. So, sorry, 1-dimensional problem so far. So, now we are just moving towards 2D, 2-dimensional, 2D finite element method or discretization. So, every particle has got 2 degrees of freedom. So, it is a 2 degrees of freedom, 2 degrees of freedom per node. So, 2D, first thing, displacement field. Of course, we have got all the relationship like strain displacement. So, first of course, you will have to deal with. So, let us start with a situation which is plane stress. So, plane stress, you should know first of all the theory. You should not jump into finite element unless you know the basic theory. Fundamentals must be known, and this is the beauty of our numerical method. You have to always start with the basic fundamental starting point. You cannot start with in between. Like mathematicians try to solve del square del force W equal to P by D. Final equation of deflection of plate is partial derivative, I mean del force W equal to P by D. That is, after so much of manipulation you have got that final equation with boundary condition. So, mathematician will not worry how that equation has come. He will just take that equation with boundary condition and try to solve it, but no, not we, not numerical analysis. You must start always from step number 1, fundamental. So, numerical method has not given you a facility of forgetting your fundamentals. This is a good method. It will always start, you have to have basic fundamentals intact. So, plane stress problem, first of all, how are the strain displacement relations related? Plane stress. So, which are the strains that are after displacement, every particle has got two displacement u and v. So, what are the, you have strains. How are the strains defined? For example, epsilon x strain in is du by dx, simple. Epsilon y dv by dy, gamma xy du by dy plus dv by dx. Any other strain that is present? No, only 3 strains. Plane stress, we have only 3 strains, that is. So, this can be expressed, this strain L and U. So, I can express this in matrix form epsilon x, epsilon y, gamma xy. That is why the theory was first written in matrix form. All elasticity equations, all theory of elasticity, theory of structure analysis, soil mechanics, they were converted into matrix. So, this can be written in matrix form, and this is we get here 3 by 2, and everything can be expressed only in terms of the two displacements u and v. So, what is this derivative? Here it is delta by delta x. Here it is 0. Second one, here it is 0, here it is delta by delta y. Third one, gamma, gamma 1 is here delta by delta y and del by del x. Is it not? So, this is, I think I have explained to you the finite element. First you have to write down your strain displacement relation in terms of continuum displacement. So, this is exact relation, this is not you are doing, it is for 2 dimensional plane stress 2D. So, then this can be written as, this matrix is called what? Derivative matrix L. So, this is your L, you have established L here. This is your L, L for plane stress, L means operator matrix, and this is your U. Now, U is not a single quantity here, it is a vector. U of any particle P consists of 2 scalar quantities, U in x direction, V in y direction. Okay. So, it is a vector. So, this is L times U. Form remains the same, but the meaning changes. So, you get first, this one has been established for the plane strain. Similarly, for plane strain and generalized plane strain, you please do this L matrix. So, first you have to do L matrix. Then next, constitutive relation. You see, these are some standard things, for plane stress, plane strain, constitutive relation. How do you write down constitutive relation? Constitutive relation. Stress to strain or strain, but then as I told you that in finite element the relationship stress in terms of strain is useful, we always, but then writing down directly that relationship is not easy. So, constitutive now, so far we are not talking of the element type. So, the constitutive relation is this is given by, then this one first strain can be written in terms of stress easily. So, we should always start like this. So, if sigma x, sigma y, what are the other stresses that exist? Tau xy also exists, sigma z also exists in plane stress, but then these are the strains. So, this one is given by, if it is a material is homogeneous isotropic, So, at any point it is isotropic. So, you have only E and nu, only two, but this can be written for any type of material, that you must keep in mind. So, you can write here if sigma x is applied, so minus nu times here it is no shear. When sigma y is applied, so 1 by E sigma y, this will produce a negative strain. So, nu by E and here 0, and when tau x y is applied, sigma x sigma y and tau x y, when tau x y apply shear stress, then this will produce tau x y by g, but no normal strain in y, no normal strain, because in isotropic material it produces the only corresponding strain. So, this is the state. So, yes.
So this is plane strain or this?
Whatever I have written is plane strain. Are you sure? No. It is plane stress. There is slight difference that you have to see, but here whatever I have written is plane stress, sigma z is 0 here. I have not written plane strain. Okay, plane strain will be slightly different from 3 dimensions. So, I am deriving directly, but even from 3D you can derive it. So, this is we are talking of this stress, plane stress at any point P, this is the stress that exists. So, this is
So, in the plane stress problem, there will be a component of strain in the z direction also.
yes, but then z direction, but then that can always be, that is dependent on the other it is not an independent quantity. Okay, that epsilon z can be found out by knowing these 3 strains. Do you know that? See, how do you get this? What is this? What is the relationship for epsilon z? Epsilon z is given by 1 by E sigma z minus nu sigma x minus nu sigma y. This is the relationship for epsilon z. Is this, have I written it correctly?
Sigma z is 0.
It is 0, but it is a general relation. Now, in the case of here in this state, yes, sigma z is 0. So, you get here minus nu by E so, this one can always be found out once you have got sigma x and sigma y. So, it is not independent. So, this is a dependent relation. This one is a dependent relation. Not independent, okay, on plane sigma x and sigma y. So, if you have got sigma x and sigma y at any point, you can always get epsilon z, and that is what, so you do not have to worry. So, this is not to be. So, now I want the relationship stress expressed in. So, you have got this S matrix is very easy here, S matrix. For example, epsilon x, epsilon y, gamma x y, which is equal to 1 by E minus nu by E 0 minus nu by E.
So, even if it is dependent, it should be mentioned in the plane matrix. So, even if it is dependent, epsilon z, so still it should be mentioned in the this vector, plane vector.
No, you think about it. Why should it mention? Honestly, at any point if you get you find out from your plane stress analysis sigma x, sigma y, epsilon s, epsilon y at each and every point. Knowing those quantities, you can get this at each and every point. You don't have to do. So, there are two types of quantities in any field. One is called dependent, other was independent. So, it is not independent. Okay. So, it will not appear in your computations. Computation means it is a trivial computation. What is this matrix? Compliance. Very good. So, this matrix is known by compliance matrix. We denote it by S. So, for plane stress, this matrix is S matrix, this is the stress matrix. So, we have got the S inverse you have to find out. So, please find out S inverse in order to express you have to only solve two equations, because third equation you do not have to solve, it is very simple. Only 2 by 2, 2 by 2 people have already solved, and so the S inverse, and this will be equal to what? C, or we are calling it also E. S inverse is elasticity matrix we are calling, stiffness matrix of the material, stiffness matrix of the material. Okay. So, S inverse that can be found out, and now we can get sigma x, sigma y, tau x y, Anybody who will give me E by 1 minus nu square? If there is a mistake, I don't remember, but I think it is correct. Nu. This is nu 1 0. This is 0 0. G is equal to, G is also equal to. So, can I, if I take this common, what will I get here? I want to get E by 2 1 plus nu, 1 minus nu square. So, 1 minus nu by 2, 1 minus nu by 2, will that do 1 minus nu by 2? So, it is 1 minus nu by. So, it is the same thing written in matrix form. So, this is the inverse of S. This one is your C matrix, E matrix for plane stress problem. Plane strain it will be different. So, please derive it for plane strain. Please derive your C matrix for generalized plane strain also. This will be the only. So, this is for plane stress. For plane strain, C matrix, please, for generalized plane strain, there also the quantities which are dependent, you do not have to worry. Please do this. So, this will be the only difference in two dimensional, I mean in the three types of problems. Your E matrix will be different, nothing else, all other steps will remain the same. So, this is your E matrix has been established now, L matrix has been established. So, now I think we can go to the next step of what? Writing down the you have to find out strain matrix, B matrix. You have to find out E matrix has been found out, B matrix has to be found, N and B matrix. Now, N and B both depend on your shape function N matrix. Of course, N has to depend on N unless you define your N. So, shape function. So, so far we need not talk about type of element. This thing can be done, whatever I have done so far can be done for any problem that you are doing in mechanics, soil mechanics, fluid mechanics, any problem. You do not have to discuss element. You can always get your L matrix, you can always get your E matrix independent of element. Now, whatever I am doing is element specific. Depending upon the element, now you have to, this is whatever I am doing now is you have to take a element. Yes, what kind of element that you are talking about? Yes, I want to. So, the two dimensional problem, see finite element when it was developed historically, first problem that was tackled was not a beam problem, not a rod problem, but it was a two dimensional problem, plane stress problem. And it was tackled by two persons, two PhD theses were produced, one by Y.K. Chung in Swansea and another by E.L. Wilson, who has written the book E.L. Wilson and Bathe. Wilson is Bathe's supervisor, Bathe is the student of Wilson, and Wilson is the student of whom? Clough, not was, everybody is. So, Clough, R.W. Ray Clough, the first person who was involved with the finite element, coining the term finite element, 1960, and also involved in the first paper of 1956. Okay, R.W. Clough of University of Berkeley. Okay, so he took his first student as E.L. Wilson in University of California. So, he did on plane stress problem. So, this is what he did and produced a PhD thesis, very simple, which you say it is child's play now, but in those days it gave him a PhD thesis. So, same thing happened in Swansea. So, element is specific. So, the first element that was tackled was that discretized, because the simplest two dimensional geometry that could be thought of was a triangle, 3 noded. Let us have a 3 noded, you cannot have simpler than this 2 dimensional body 3 noded. Otherwise, 4 node means rectangle. So, triangle is the simplest. So, a triangle was assumed. Triangular, and that is why it is called triangular element. So, triangular element, now we are talking of a 3 node it is very simple, although I am taking lot of time, but so you have to first of all number your 3 nodes in some manner. Now, you have to be careful. You see, in a line element, we were always numbering from left to right. There was only one direction, x, in the positive x direction, as you move from this x to next x, but positive direction, left to right. Now, in 2 dimension, how to number? You have to devise a method. Otherwise, one element you will number like this, next element like this. No. So, it was devised that you must number them anti-clockwise. From anywhere you start, does not matter. but you number them anti-clockwise. And then node 1 will have a displacement, 2 component of displacement. Every node will have 2 degrees of freedom. So, it will be, let us call them as u1, v1. Node 2 again will have u2, v2. Node 3, u3. So, with this element has got 6 degrees of freedom, not 1 or 2, like the bar element had only 2 degrees of freedom. This is okay. I am seeing. So, this has got 6 degrees of freedom. So, you have to express this 6 degree of freedom, and this is a particle p inside continuum displacement. So, you have to express this in terms of the continuum displacement of particle p, which is only u and v, any general displacement. So, how to relate u and v of particle p to in terms of 6 DOFs, degrees of freedom. That is what is the crux of the matter. You must be able to express u and v within the element moving any point in terms of 1, 2, 3, because that is the first step. And that too, now 2 dimension, I know it very clearly, yes, it can be written. Yes, it is n1 u1, n2 u2, n3 u3. Reed's method, it is applied to any field. If you know 3 particles, I can always get anything. But then what is the value of n1? N1 is a triangle. I will stop with this. Let me make a triangle, and then I will stop. First I should get a square, correct square, then only I can have perfect triangle. Yes, this is a triangle. So, let us say these are the 3 nodes. These are the 3 nodes of 1, 2, 3. 1, 2, 3. What is your shape function 1? Keeping u2 this 0, this should have unit value. So, this, what is the shape of this? It is the equation of plane of this inclined plane. This is unity. So, a triangular plane will simply remain plane. The equation of this inclined plane is the shape function. What is the shape function of node 2 is this. Lift this by unity keeping this. So, this is the physics of the meaning of shape function. Shape function can be derived, I mean at least you should understand what is shape function. Node 2. Node 2 has got shape function and node 3 has got. So, they will all be the equation of the plane of this inclined plane, and that we will see tomorrow. Okay, so, we will stop here.